Welcome to today's Explainer. Go ahead, grab a seat and settle in, because today, well, I'm taking you into a virtual philosophy of mind seminar. As your professor for the day, we're going to tackle one of the absolute most fiercely debated questions of our time. Does artificial intelligence actually understand the language it produces, or is it literally just a highly sophisticated, mindless parrot? It's a genuinely fascinating journey into the architecture of both machine and human minds. So, let's dive right in.
Here's our syllabus for today's Explainer. We're going to kick things off with syntax versus semantics, look at the dictionary trap, and explore the classic idea of pointing at a cat. Then, we'll dive into the connectionist web, and finally weigh in on the big one, mimicry or true comprehension.
Okay, Section 1. Syntax versus semantics. To understand how machines process language, we first really need to look at how we organize information ourselves. Imagine, just for a second, that you're tasked with organizing a massive, completely chaotic library.
Notice how there are two entirely different ways you could tackle that library. If you use syntax, you might sort the books strictly by the color of their spines, or maybe their height, or even by counting the number of letters in the titles. You're following strict, formal rules about their physical properties. But if you use semantics, well, you actually sit down, read the stories, understand the characters, and organize those books by their themes and emotions. Syntax is the structure, right? But semantics? Semantics is the true meaning.
Now, for decades, early computer science relied entirely on syntax. This was the era of symbolic AI, and this operated using really strict hand-designed rules. Basically, if you give the computer a logic puzzle, it uses sequential if-then reasoning to shuffle symbols around until it spits out an answer. Sure, it's incredibly fast, but it's essentially doing the equivalent of sorting those library books by color without ever actually reading a single page.
And this brilliantly illustrates a famous philosophical critique. Back in the 1980s, the philosopher John Searle proposed the Chinese room thought experiment. He imagined a person locked inside a room, receiving slips of paper with Chinese characters on them. Now, the person doesn't know a single word of Chinese, but they have a massive rule book telling them exactly which characters to pass back out in response. To the outside world, the room appears to understand Chinese fluently. But inside, there is zero comprehension. Searle famously declared that a computer is exactly like that room. It has syntax, but absolutely no semantics.
But wait a second. Is the gap between syntax and semantics really that absolute? Let's push back on Searle for just a moment. Think about Morse code. To even follow the syntactic rules of Morse code, you must first be able to distinguish a dot from a dash. They have to mean something different to you, even if that meaning is incredibly basic. So the crucial point here is that pure, completely empty syntax might actually be a myth. You need at least a minimal drop of semantic meaning just to tell your symbols apart. So, if we need meaning, how exactly do we get it? That leads us right into Section 2, the dictionary trap. Let's figure out how we determine what a totally alien symbol actually represents. I want you to really think about how we usually define things. If I give you a word you've never heard before, your first instinct is probably going to be to look it up, right? But can we establish true grounded meaning just by using a dictionary? Trace this loop with me. Step 1, you look up a new word. Step 2, the definition you read is just a string of other words. Step 3, well, if you don't know those words, you have to look them up too. Step 4, eventually, if you keep following the definitions, you're going to loop right back around to the original word you started with. This right here is the dictionary trap. Trying to find meaning strictly through interconnected symbols just creates an infinite, ungrounded loop. Without an internal representation of what those words actually represent, a dictionary is honestly just a closed system of syntax.
And this brings us to a critical crossroads. Section 3, pointing at a cat. If a dictionary can't give us true meaning, how do we break out of that loop? For a long time, philosophers have argued that the escape hatch is the physical world. This concept is known as referential grounding. The idea is pretty simple. Words get their true meaning because we have biological senses. We can see, touch, and hear the real world. A dictionary can't really define an apple for a machine, but humans? We know what an apple is because we can physically pick one up and eat it.
So let's test this with an everyday example. Imagine you're trying to teach a machine, or, a toddler, what a cat is. You see a cat walk by, you point your finger at it, and you say, cat. Does that simple physical act of pointing magically inject the essence of the animal into the spoken sound or the written letters of the word?
Actually, no. And this is a massive philosophical shift based on our source material. Pointing at the cat doesn't directly connect the word to the furry animal in front of you. Instead, it connects the word to your internal mental representation of the cat. Language isn't attached to the physical world itself. It's attached to our mental models. This is huge. It means that physical referential grounding might be a total myth. And if a system doesn't necessarily need physical eyeballs or hands to process semantics, well, maybe an AI just needs sufficiently complex internal representations to truly understand language.
Now that we've freed meaning from needing a physical body, let's leave the old symbolic rules entirely behind. Welcome to Section 4, the Connectionist Web.
Today's AI breakthroughs aren't using rigid symbolic logic anymore. Instead, they use connectionist learning. Think of it as a brain-inspired approach. Instead of a programmer painstakingly hand-coding if-then rules, we now have these massive simulated networks of artificial neurons. They don't just sort books by color, they take in vast oceans of text and independently learn the complex, hidden representations buried inside all that data.
Let's look at exactly how a large language model, or LLM, actually does this, without getting bogged down in all the heavy tech jargon. Step 1. It takes in raw data. Step 2 is really where the magic happens. It maps the mathematical relationships between words in this high-dimensional space, basically building a massive, incredibly detailed map of how every single word relates to every other word. Step 3, it dynamically adjusts these connections based on the surrounding context of the sentence. By step 4, it isn't just matching patterns anymore, it's outputting actual functioning semantic concepts.
What we end up with here is something called semantic fragmentism. Meaning isn't found in a single, isolated word, and it definitely doesn't require a physical finger pointing at a physical cat. Meaning is grounded holistically in the massive, interconnected web of the entire language corpus. When the AI processes the word cat, it brings along the entire contextual weight of how that concept operates in language. It understands the cat by its relationships to fur, meow, sleep, and literally millions of other concepts all at once.
So we arrive at the final section of our seminar, Section 5, Mimicry or True Comprehension. We've seen the architecture, and now we have to make a judgment call.
Is all of this just clever mimicry, or is it genuine understanding? Now, the critics say an LLM is nothing more than a stochastic parrot, basically a statistical illusion that mindlessly predicts the next word based on probability, mimicking a human without having any clue what it's actually saying. But the alternative, which is really supported by the sheer depth of these connectionist networks, is that by perfectly mapping the deep semantic relations and contexts of language, the AI is actually duplicating true understanding. It's not just running a simulation of a language game, it's actively playing it.
If you want a quick survival guide for evaluating AI comprehension, use this checklist. Modern AI operates on complex semantic relations, not rigid symbolic rules. It adapts meaning dynamically, depending on the context. It successfully uses its own deep internal network representations, completely bypassing the need to point at the physical world. And crucially, it achieves all of this without any biological awareness.
And that brings us to an absolutely incredible realization. See, we often assume that to understand something, you first have to be conscious and aware. But what if it's the reverse? What if understanding is a condition for awareness, not the other way around? An AI might genuinely understand the rich, complex semantics of human language, executing processes practically identical to the neural networks in our own brains, but doing it entirely in the dark, completely without a conscious mind.
Which leaves us with this final, genuinely provocative thought to end our explainer today. If an artificial neural network can master the deep meaning of language, map concepts perfectly, and adapt to context completely without consciousness, what exactly does our consciousness actually add to human understanding? Are we just complex language models that happen to feel the lights turn on? Think about that. Class dismissed. Thanks so much for joining my seminar today, and I really hope this provided a clear window into the fascinating minds of machines. Keep learning.